Hi everyone. In this video we're going to discuss the implementation of cascade, ratio, and feed-forward control to improve the performance of a feedback control loop. Okay, so the objectives of this lecture are going to be to look at different ways that we can implement certain types of control strategies to eliminate the effect of a specific disturbance. So we're going to look at these three different methods. They're each a type of feed-forward control, and they're used to eliminate the effect of a specific disturbance. So your objectives, based on the content of this lecture, are going to be to design a process control scheme that implements one of these strategies in order to eliminate the effect of a specific disturbance. And also what you'll need to do is look at a process that has one of these methods already implemented and discuss what the effect or what's the intended use of this feed-forward control mechanism, which disturbance it corrects for, and how the process uses this method to eliminate the effect of a specific disturbance. We'll also do things like look at, do the logic flow through the system. So a change is made, which system acts first, which system responds second, accordingly. Okay, so the content of this lecture is going to come from Chapter 12 of Chemical and Bioprocess Control, the 4th edition textbook by James Riggs. Okay, so in this chapter, we're going to discuss the use of these techniques to eliminate a specific disturbance. So when we talk about cascade control, so cascade control reduces the effect of a specific disturbance, and this is a specific disturbance that we can reduce the effect of by changing the manipulated variable. So for cascade control, the disturbance should be located around the manipulated variable. In other words, the manipulated variable will be changed to eliminate the effect of this specific disturbance. Ratio control is another type of feed-forward in which ratio control is used to reduce the effect of a feed flow rate. So when there's a change in a feed flow rate, we can measure that flow rate, and then the controller can take a corrective action to eliminate the effect of that change before the process itself is unduly affected. And then the final method is called feed-forward control. And this is a generic control that's added as a feed-forward method that's independent of the feedback control loop. So when we talk about feed-forward control as a specific method, feed-forward control is going to be its own controller, whereas cascade and ratio will be incorporated within the feedback control loop. Feed-forward control is a specific control that's added to feedback control. So there's two loops that are added together to change the manipulated variable for that process. So the purpose of all of these methods is that when a disturbance affects the process, a corrective action takes place by measuring the disturbance before the actual control variable is changed or is significantly affected. So this plot shows an example of how your control variable may change when you incorporate some type of feed-forward control. So if we look at this first figure shown here, when we have the process tuned in feedback control only, okay, and so I want to point out, so in feedback control you can see that the process changes quite a bit, or changes by a decent amount, and then the controller starts taking a corrective action to bring the temperature back down to the set point, and then there's sort of a little bit of oscillation in order to achieve the aggressiveness in response. Again, if we just look at this general control for this feedback control only process, one of the things we might notice is that the oscillations don't occur around the set point. So we could do a better job tuning this controller. So my question for you is, how would we retune this controller in order to achieve better process? Why don't you pause and think about that for a second, and then I'll discuss. Okay, so my points here, the things I want to point out here is, if we look at what in general the decay ratio is for this process, looking at the second peak to valley over the first peak to valley, we can see here that we have about quarter amplitude decay or maybe 1/5 amplitude decay. So the aggressiveness of the process is good. What we notice is that the oscillations aren't around the set point. So therefore, one of the things that we're going to need to do is we're going to need to decrease tau I, and we'll decrease tau I to get the oscillations around the set point. But also what we know is that when we decrease the tau I, it's going to make the oscillations, or it's going to make the decay ratio larger, which means is that the controller is going to be a little bit too aggressive. Because of this, what we'll also have to do is decrease the value of the gain in order to achieve the decay ratio we want with the oscillations around the set point. Okay, so now that we're done with that tangent, let's come back to discussing the effect of feed-forward. The second curve right here shows an example of the same type of feedback process that has a feed-forward mechanism incorporated into it. Since this is just generic, we're not talking about the specific method yet. In this case, what we can see is that when we correct for whatever the disturbance is, the process doesn't significantly change away from its set point. Also, again, in this case, the controller, it has the same type of tuning parameters, but now in this case, the oscillations are around the set point because the corrective action was taken a little bit earlier due to the feed-forward mechanism. Okay, so let's talk about how does this feed-forward mechanism, or what are possibilities that this feed-forward mechanism can be used in order to achieve this improved performance. Okay, so in a system in which we care about temperature, it could be something like a heat exchanger or a reactor. And in these cases, we have things like coolant flows, we have steam pressures, we have other things that are affecting the process for a system where we're trying to maintain at a specific condition. So for example, if we have a coolant flow and the temperature of the coolant flow changes, we could measure that coolant flow temperature and then adjust the coolant flow in order to achieve the same type of cooling that we need. If we know that there is a change in the steam pressure, so for example, there's something that happens upstream and our steam supply pressure changes, that's going to affect the temperature. Therefore, we can apply a feed-forward mechanism to make sure we're achieving the same heating before the process is unduly upset. But again, it's important to note that the strategy for the feed-forward type is going to strongly depend on the disturbance. So that's something that we're going to focus on in the discussion of the upcoming methods. Okay, so this example, we're going to talk about level control in a tank with and without cascade control. And we'll use this example to introduce what cascade control is. Okay, but first, before we start, when we think about our process objective, let's look at this top plot up here. When we're controlling the level in the tank, we have, in this case, our manipulative variable is the flow out. What we're controlling is the level in the tank. We have our specified level, and so we're going to measure the level, and the controller is going to compare that to the set point, and the controller is going to open or close the valve to keep the process where we want it to be. Okay, so in this process, there are a variety of disturbances. And what a disturbance is it's something unrelated to the manipulative variable that affects the control variable without the process. So let's think about what are some type of disturbances that can affect this process. Why don't you pause and take a minute to think about it and identify these disturbances, and then we'll come up with a cascade control scheme in order to minimize the effect of that disturbance on the process. Okay, so now disturbances for the system. Some of the things that I can think about are we can have a change in inlet flow. Okay, so if there's a change in inlet flow to the process, it's going to cause the level to increase or decrease. Then we'll detect a change and then the outlet valve will change. But in that case, feedback only control, the level itself has to change before the controller takes action. Another type of disturbance could be the temperature. Again, the temperature could cause a change in density, which causes a change in level, but that would be very small. The effect would be minimal. Other disturbances could be related to the outlet flow. So we're controlling the outlet flow based on this valve. But what we know is that the flow through this valve can change without us changing the actual valve position, which is what the controller is going to do. Okay, so if the level stays fairly constant, the pressure, hydrostatic pressure from the tank level is going to be constant, but the downstream pressure from this valve could change, which would cause the flow to change. So another disturbance could be the downstream pressure. The downstream pressure would cause the system to change. All right, so we said for cascade loops is that the disturbance has to occur around the manipulative variable, or the manipulative variable has to be able to change to correct the disturbance before the process is upset. If we look at this case right here, if we think about the disturbance as the feed flow in, if this feed changes, this flow is not around our manipulative variable. right? So we can't make a change to the process based on this measurement. And actually, when we'll talk about ratio control, we'll talk about using ratio control as a way to take care of this. So the disturbance that we care about in this case is going to be the downstream pressure, right? So if the downstream pressure changes, it's going to cause the flow to change, which is going to cause the level to change, right? So that's the point of the cascade scheme shown here on this plot. Okay, so what we see is that in this case now, the way cascade works is that we're going to measure the flow through this valve. Okay, so the flow that's going through this valve, we're going to measure. Okay, so again, let me just point out first is that when we incorporate some sort of feed-forward control scheme, the first thing we always want to do is draw our feedback loop, right? So the feedback loop is, again, our main variable is this level in the tank. So level in the tank is our main variable. Okay, so we're measuring the level and we have a level set point. Okay, this is the primary control objective. And then again, we can kind of just make a dashed line to show this going to the manipulated variable. Right, that's the first thing we want to do. Okay, the second thing we want to do is identify the disturbance and then measure the disturbance. So the disturbance is the flow out based on the change in pressure downstream. I mean, we could make it the pressure, but again, we're going to measure the flow. So we'll measure the flow, and the way Cascade works is we'll have an inner controller. So we measure the control, that value is sent to a controller. Now remember, for a controller, what a controller needs is a measured value and it needs a set point. So the way Cascade works is that the primary control objective, which is the outer loop, is going to send a remote set point to the inner controller, and then the inner controller is going to change the valve position. Okay, so let's discuss a little bit how this works. If there's a change in flow through this valve with the level not changing, okay, the level is going to be constant, the level set point is not going to change, so there's going to be no signal coming from this point. But eventually we know that if this flow changes, the level is going to decrease, and then this is going to take corrective action, but it's not going to happen until the level decreases. But immediately when this flow changes, we're going to detect a change in flow, and this inner loop is going to measure. So this inner loop has a set point already. If we detect that the flow decreases, for example, this controller is going to tell the valve to open up so that the flow gets back to the remote set point value that's set by the inner controller. Eventually there's going to be some disruption to the main process, and this controller is going to account for those types of changes. But again, with this inner loop, we are able to take advantage, we're able to correct for the disturbance before the process changes significantly. Okay, so the main requirements for Cascade control to be successful is that the inner loop must be capable of reducing the effect of one or more specific disturbance. Right? So what that means is that the inner loop is going to use the same manipulated variable as the outer loop. And so what that means is that the manipulated variable has to be able to correct for changes in the disturbance before the process is changed. The dynamics of the inner loop should be at least 3 times faster than the outer loop. So the inner loop is often a flow control loop. So oftentimes when the primary control element is a valve or a control valve, the control valve is oftentimes cascaded. In this case, the inner loop can be tuned aggressively. So what this means is that whenever there's a change, the inner loop can be very aggressive. And it can also be P-only control, because the inner loop is just trying to get us to respond before the process changes too much. The outer loop is going to do the work in eliminating the offset. So by having a P-only control, we can have a faster response, and then we don't need to worry about offset because the outer loop is going to take care of the offset for us. So this is something that seems a little bit counterintuitive, but you have access to Control Station Loop Pro, so you can test this idea or test this concept in Control Station. So in Control Station, there's a Cascade reactor that you can look at. On this loop, what I want you to do is tune the inner controller for P-only control, and then tune the outer controller for maybe PI control, and you can see there that the P-only controller on the inner loop is going to be able to respond and eliminate disturbances faster than if it were a PI only loop. I think we might look at this on an assignment a little bit later. Okay, well, let's look at another example. So this is an example of a reactor that incorporates cascade control. So again, the first thing so if we look at, okay, let's look at this figure right here first. Okay, so if this, for feedback control only, here's our temperature controller, we need a specified value. The objective of this feedback control loop is we're measuring the temperature. So the thing we care about is the outlet temperature. And again, the outlet temperature could be inferring the composition, but in this case, we're controlling the outlet temperature. We have the controller, and we're going to maintain the outlet temperature by controlling the flow of cooling water to the system. Okay, so in this case, we're going to specify a temperature, and the temperature controller is going to change the flow of cooling water to keep us at the target temperature. So in this case right here, let's start by identifying some disturbances. So this would be a good time to pause the video and identify some of the disturbances that can cause a change to this outlet temperature without anything associated with the control loop changing. Okay, so hopefully you came up with some of these ideas. So some of the disturbances to the system can be associated with the feed. So we could have a feed flow, or we could have a feed temp. Those would be two different disturbances. Other types of disturbances could be related to the cooling water. So the cooling water flow could change without the controller changing the valve position. And also the cooling water temperature could change. Okay, so if our objective is to incorporate a cascade scheme, remember that the cascade scheme has to be able to correct for the disturbance using the manipulative variable. Okay, so for changes associated with the feed, in this feed, the manipulative variable isn't located around where these disturbances are. So we wouldn't correct for changes of the feed flow or the feed temperature using cascade control. We would correct for changes associated with the cooling water because the manipulative variable is located around the cooling water. If the feed flow changed, we might use ratio control, which we'll talk about later. Or if the feed temperature changed, we might use feedforward control, which again, we'll talk about in a few slides. Okay, so we'll try to eliminate the effect of either cooling water flow or cooling water temperature on this process. And so the way this can be done is, again, what we need to do is we need to incorporate an inner loop. So again, the first thing that we need to do to design the cascade scheme is we first start with our primary control loop. So we have our sensor, we have our controller, we have our specified value, and again, if I just kind of dash this through, our feedback only control loop is going to look like this. Okay, so in order to incorporate a cascade loop, we need to measure for a disturbance that's going to affect the process and have the manipulative variable change in response to that disturbance before the temperature changes. Okay, so what we know is that if the properties of this, or if the temperature or the flow of this cooling water changes, what's going to happen is that it's going to change the temperature of the cooling water in this jacket. Okay, so we can measure that. In this case, we're going to measure the temperature of the cooling water, and then this temperature is going to be sent to a controller, and now the inner control loop is going to be what changes our manipulative variable. And then again, our primary control loop is going to send the remote set point to the cooling water. Okay, so we draw our outer loop, see how that responds. Then we measure for the disturbance, and then again, there's a variety of ways that this can be done. We're measuring the temperature of the cooling water because we know that the temperature, if the flow changes or the temperature of the cooling water changes, it's going to affect the temperature of the water in the jacket. And it's the temperature of the water in the jacket that affects our control variable, not necessarily the temperature of the water coming in. So that's what we want to measure. So this temperature is going to go to the inner loop controller. The inner loop controller is going to change the valve, and the outer loop is going to provide the set point to the inner loop controller. So let's think about how this might work in practice. Or we'll come back to the feedback only. If the cooling water temperature decreases by, let's say, 5 degrees, what's going to happen is that's going to cause the temperature of the jacket, temperature in the cooling jacket, to decrease. When the temperature in the cooling jacket decreases, it's going to result in less cooling, or it's going to result in more cooling. For the lower cooling water temperature is going to cause the temperature of the product to decrease. Therefore, this feedback control loop is going to ask for less cooling water. So this controller is going to tell the valve to close a little bit so that the temperature of the cooling water is going to increase a little bit, bring this back to the target value. All right, with this cascade loop, a decrease in cooling water is going to cause the temperature of this in the cooling to decrease. This temperature is going to be measured before the process changes too much. And because the inner controller, so the temperature of this is going to be lower than what's being asked for by the outer loop. Therefore, this inner control loop controller is going to is going to close this valve in order to allow this temperature to heat up a little bit based on the heat transfer with the reaction system. In this case, the system is able to respond before the temperature of the reactor changes, which means that this overall reactor temperature isn't going to experience as much of a change overall. We can also incorporate multiple cascade loops together, and we'll walk through this method on the next couple slides. Okay, so let's just see how this works in general. For this bottom section of the distillation column, what we care about is the composition of the product coming out. Okay, so the composition, we measure the composition, we have a controller. Without any sort of cascade scheme, we're going to change the flow of steam to the reboiler in order to keep this composition where we want it to be. But we know that the flow of steam can be affected by the pressure of the steam, and we know that the pressure of steam is going to affect the temperature of the column, and the temperature of the column is going to affect the ratio. So it's going to affect the composition of the system. Okay, so instead of spending too much time on this slide, let's walk through how this might work. Okay, so if we want to draw the system in general, okay, so we care about the composition of the bottom stream. Our manipulative variable is the flow of steam to the reboiler. So what we can do is we can draw a composition controller, and this is going to change the flow, or this composition controller, based on changes in the composition, is going to tell the steam controller to increase or decrease the amount of heating to the reboiler, and that's going to affect the composition. So that would be the distillation column, bottoms of the distillation column, without any sort of cascade control, feedback only. And I suppose I should say specified here. So again, this is feedback only, as shown here. Okay, what we know though is that the disturbances, again, if we want to think about what are some of the type of disturbances that can affect this system right here, we have essentially the feed flow of the steam. This is going to be affected by the pressure of the steam on the other side. We have other things like feed flow of the feed flow to the process. So for example, this stream overall, the flow of this stream, the temperature of this stream, for example, could be a disturbance that affects the process. So in all of these cases, we know that the system that's going to respond the fastest is going to be the flow around the control valve. So that's going to be one thing. Any disturbance to the system is going to affect the temperature of this column. So the flow of steam is going to affect the temperature of the reboiler. It's going to affect the temperature of the column, which affects the composition of the products. So we can incorporate multiple cascade loops to eliminate the effect of a variety of these different types of disturbances. We can eliminate effects associated with steam flow by having a cascade loop around the flow controller, and we can incorporate disturbances associated with a variety of other processes that affect the temperature of the column by putting a cascade loop on the temperature of the column. Okay, so the slowest loop is the composition. So composition is the slowest. So this is going to be our outer loop. The next slowest is going to be the temperature. So in this case, as shown here, we're measuring the temperature on the column, and then the temperature on there's going to be a controller that compares the temperature to a remote set point. Okay, so when we cascade the composition to the temperature of the column, and again, this would be the temperature of a specific tray on the column. In this case right here, now this internal controller could tell the valve to open or close. Okay, so this would be a composition controller cascaded to a tray temperature controller, and this is going to tell the valve to open or close. So this cascade loop is going to reduce the effect of whatever disturbances affect the temperature of the column, and that could come from changes at the top of the column, changes in feed flow, feed composition, etc. And now finally we can incorporate a cascade loop around the controller, okay, or around the manipulated variable, because there's aspects of the steam pressure and steam flow that can affect the flow of steam without anything else that we talked about changing already. So in this case, now we would have to measure the steam flow, so shown here, so we measure the steam flow. If we measure it, the inner loop also has a steam controller, so we measure the flow, that's the controller is going to take that measurement of the flow, and now in this case, let me maybe erase this line. The temperature controller is going to be cascaded to the flow controller, so this temperature controller is going to send a remote set point, and then the flow controller is going to change the valve to the system. So this loop is going to eliminate the effect of disturbances associated with the flow of steam. This loop is going to eliminate the effect of disturbances associated with the tray temperature in the column, and then we have our primary control loop, which is going to make sure that the composition stays at the desired set point. All right, so next thing we want to talk about is ratio control. So ratio control is a specific type of control that's useful when the required value of the manipulated variable, so when the required value of the manipulated variable is proportional to a feed rate to the process. So the important thing for ratio control is it's only used when the disturbance, this is important, when the disturbance is a feed flow. But just because the disturbance is a feed flow, it doesn't mean a feed flow as a disturbance will always be compensated for using a ratio controller. The disturbance has to be proportional to the required value of the manipulated variable. So that's the important thing for ratio control to be useful. And again, we'll go through a couple examples. In ratio controller, it's going to work similar to cascade control, in that the controller output of the primary loop, so this is going to be the primary CV control loop, is going to output a ratio. In this ratio controller, it's going to take the ratio, and it's going to take the measurement of the feed flow rate, and it's going to tell the manipulated variable to change accordingly. So a ratio controller is a specific type of feed forward. Okay, so the other thing that's important is oftentimes the feed flow to the process can cause a change that occurs that doesn't affect the process right away, but the process is slowly affected by the disturbance. So in the case where the disturbance has a slow effect, we can use what's called dynamic compensation. And this is essentially like adding a filter or a first order lag component to slow down how the control variable, or how the manipulated variable changes in response to the measured change in the disturbance. So again, main thing is the disturbance is a feed flow rate. So let's consider the example. I'm going to draw down below. Let's consider the level control, which we talked about previously. Okay, and for a level control, last time we talked about doing cascade control on the level controller. In this case, we had the disturbance located around the manipulative variable. Okay. If our disturbance to the system is the feed in, we know that changes in this feed flow rate are going to cause the level to change. So we can account for these changes in the feed flow rate before the process is affected by using a ratio controller. Okay, so again, feedback, the level control, or if we're controlling the level, we're going to measure the level, and we have a specified value, change the system. But again, if we know that the feed into this process is the primary disturbance, the way we can use ratio control is we can measure this. So we would have FT. So a disturbance says that the ratio controller is going to be a ratio. So the ratio controller, it's going to be, it's going to be a ratio. So the controller is essentially just going to be a constant value where we take the measurement of the feed flow and we change the manipulative variable. So for the ratio controller now, the primary control loop is going to set a ratio. Okay, so this controller is going to set a ratio, and the ratio controller is going to open and close the valve. Right? In this case right here, essentially the ratio controller should be a ratio of about 1. Okay, if we're specifically setting the flow, because to keep a level constant, this flow is going to change. If this flow increases, we know that this flow needs to increase by the exact same amount to change the controller. So if the controller is based on the flow, the ratio would be 1. If the controller is based on a valve position, now we have to correlate the valve position with the flow coming into the system. All right, so let's look at an example. So here's a ratio controller for a wastewater system. Now, in this example right here, I tried to gray out this cascade loop. So this system right here, it's an example from the textbook. It has a cascade loop associated with the feed flow of the base solution. Okay, when we neutralize acid wastewater, we know that the amount of base we need should be equal to the amount of acid that's coming in. Now, if the concentration of the acid and the concentration of the base are different, then there's going to be a ratio based on what those concentrations are. If the concentrations are the same, then the flow rate should be equal. Okay, again, because we're talking about ratio control, the primary disturbance right here is going to be the flow. If we want to account for changes in the acid concentration, we're going to need to incorporate a different type of control, and we'll be able to think about what that might be after we finish this lecture. Okay, first we want to say in feedback only control, again, our main disturbance is, or our primary control variable is the pH of the system coming out, so we want to keep that pH at a certain value, and probably it's going to be something that we can just discard. We also need to have a pH set point or specified on the controller. In feedback only control, what's going to happen is we're going to measure the pH of the system, and this is going to tell the valve to open or close. Okay? But because we know that the flow of the acid wastewater might change, we can have the system change the flow of the base before the pH of the overall system changes too much. Okay, and we do that by incorporating a ratio controller. Okay, so now instead of this system changing the valve, the pH controller is going to set a ratio. So we're going to have a remote set point, and that's going to be a ratio. And the ratio is essentially for this system going to be the ratio, or it's going to be related to the concentration of the acid and the concentration of the base in the sodium hydroxide solution. So in this case, because the flow is a disturbance associated with the wastewater, we have to measure that. So we measure the disturbance. The disturbance goes to the ratio controller. the primary control loop sets the remote set point, and now in this case, the ratio controller is going to change the valve position. Okay? So we have the cascade loop here because there could be disturbances associated with the feed of the sodium hydroxide solution. We don't really need to worry about that for now in terms of this ratio controller. So we're gonna, for this discussion right here, we're gonna ignore that this ratio is here, and we're just gonna say that the ratio controller is gonna open or close this valve. Okay, so if we want to consider how this actually works, in practice, we know that as soon as this flow changes, we want the flow of the base to change. Therefore, we don't need any sort of dynamic compensation. Okay, so without the system, without the ratio controller, an increase in the acid wastewater flow would cause an increase, or it would cause a decrease in pH of the system. Therefore, without the ratio controller, the feedback loop would ask this valve to open to send more base. When we can specifically, with the ratio controller, if the flow of the acid wastewater increases, right, this ratio controller is going to automatically ask for an increase in control, because the way this control works is it's just going to ratio this feed flow to this ratio set by the primary control loop, and that ratio is going to tell the valve to open up right away. All right, some things you might notice in the system is that if both of those flows increase, the level in the system will increase. So probably in this system there's going to be a level control that's based on the flow of the effluent coming out of the system in order to keep the level at a fairly constant level. Okay, so that's how ratio control works. If in some cases the feed to the system might slowly affect the process, and in that case we need to consider dynamic compensation. So what dynamic compensation is it's going to be an element of the control scheme that's going to essentially delay the time which the measured signal goes to the ratio controller. Okay, so again here, the feed to the heating steam is set up in cascade control. But what I want to do right now is I'm going to just ignore the cascade right now. Okay, and what we're going to say on here is that in this type of system, the primary control objective is the composition, because we're purifying or separating using the distillation column. So the main thing we're trying to do is measure the composition and keep this at a specified value. So the way the feedback system would work is, as we discussed earlier, measure the composition controller compares that to the set point, and this will tell the steam valve to increase or decrease to keep us where we want to be in terms of composition. If we know that the feed rate to the distillation column is our primary disturbance, we can measure that, and the feed to the system is going to set a value, or the feed is going to be measured by the controller, and this controller is going to, the ratio controller is going to cause the system to change based on the change of feed into the system before the composition changes too much. However, when the feed to the column changes, we know that it takes a while for the temperature to change, for the composition to change. So the time scale at which we want this valve to open is going to depend on how long it takes this feed to actually cause a change to the system. So in the case of the acid wastewater, the change is going to be immediate, right? So we want to change the base flow immediately. In the case of the distillation column, if this feed increases, where we need to achieve more heating, we don't want that temperature, we don't want the heating to increase right away, because if the steam flow to the system increases right away, it's going to increase the temperature of the bottom of the column. Okay, so there's going to be some sort of lag that's associated with the change that occurs to the system. So instead of this value going directly to the ratio controller, the measurement's going to go to a dynamic compensator, and that's going to go to the system. And so you can think about this as like a filter, right? Remember when we had a filter, what that filter did is it averaged a bunch of values, and it had lag that went to the actual system. So the dynamic compensator could act like either a first order lag element or a filter to the process. In the case of if we think about how the filter works, as we're averaging a variety of these types of these values, when the feed flow to the column increases, that measurement coming out of the dynamic compensator, which is averaging a lot of different values that were before the change was made, this compensator is going to cause a gradual change in the feed flow to the system because it's measuring a lot of values that were before the change was made. Once the values are averaged, once all of the values are primarily based on the change, then this will be at the new value. Or then the feed flow will be at the value in which the correct amount of heating is required to compensate for the change in the feed flow. During this time, however, we would expect changes to occur in the system. So the temperature of this column is going to change and the composition will change, but because we have measured this change before it affects the process, we're able to prevent the composition from changing too far from its targeted set point. So the final feed-forward strategy that we're going to talk about is the generic feed-forward strategy. So in this slide, we're going to look at feed-forward control by itself, feedback, and then the combined feed-forward feedback control to eliminate the effect of a specific disturbance on the process. Now, feed-forward, again, is used for specific types of disturbances that can't be compensated for using ratio or cascade control. In the system that we're going to look at, we're producing steam in a steam drum. Okay, so the way this works is we have a tank that's heated. There's going to be liquid water, steam at the top, and so steam is going to be pulled off by users. As steam is pulled off by users, makeup water is going to be added to the system to keep the water in the system at a specified level. So the way the system would work in feedback only control is, for level control, we measure the level. Okay, the level is going to go, the measurement of the level goes to the level controller. That's going to be compared to the set point. And based on the level in the system, we're going to add makeup water to the system. We don't really expect the level to increase. The level is only going to decrease as we pull off steam. Okay, but one of the things that we know is that as users pull steam off of the system, the level is going to change. What that means is that as the steam is being used, the level is going to decrease before any sort of corrective action is taking place. But what we know is that as this flow increases, we're going to need to increase the flow of makeup water to the system. So we could run this system using pure feed-forward control. For pure feed-forward control, we measure the flow coming off the system, and then the feed-forward controller is going to tell the valve to open or close. Okay, so again, as this flow changes, the flow of makeup water is going to change to account for the amount of steam that's being used. If the flow of steam increases, this controller is going to tell this valve to increase. If the flow decreases, it's going to tell this valve to decrease. Okay, so the problem with feed-forward only control is that we don't have a measure of the steam in the system. If we can perfectly measure the flow of steam and then perfectly set the flow of makeup water to the system, then this level here should never change. But in real systems, what we know is that we don't actually have perfect measurement of the flow, and we also don't have perfect correlation of the measurement of the flow of steam to the valve position on the control valve, because again, there's not the gain on a flow valve the gain on the flow valve changes depending on the valve position, and that's something that we saw early on when we looked at designing control valves for these systems. So in order to come up with a system that works the best, is we can incorporate feedback and feed forward together. Okay, so again, the feed forward control is going to be added to the feedback control. So we have two loops that are going to be added together. Okay, and these are going to both work independently and they're going to add together. And this isn't going to be a problem because in the event of no change in level. So if this level right here stays constant and we measure an increase in the flow coming out, this feed forward is going to tell this valve to increase. Right? No change here, increase here, the valve's going to increase. But eventually, so because there's not a perfect correlation between these two, right? No change in this valve here, eventually this level might decrease or increase a little bit relative to the set point. If this level changes and there's no change here, this controller is going to tell the valve to increase or decrease. So again, it's going to change this without anything happening here. So the feedback control loop is going to make sure we stay at our set point of the level. The feed forward loop is going to cause the valve to change before our process significantly changes. This is going to keep our steam drum at a nearly constant level, more so than if we had feedback only. And for the case of feed forward only, it's going to prevent the tank from completely emptying or filling up entirely because of small errors related to the measurement of the flow and the setting of the valve position. So if we analyze a little bit about how this works, so in this case, the feedback loop, it's going to absorb variations. So if we have the system in feedback loop, it's going to absorb variation in the steam usage by feedback alone. We discussed what that was looked like. For feed forward can handle variations in steam usage, but the problem with feed forward only is that small errors in metering will eventually empty or over the flow of the tank. Feedback will work, it just won't keep us, we would just expect the level in the tank to change as the steam usage changes. Feed forward will keep the level from changing significantly, but eventually it could cause the tank to empty or fill up. So the combined feedback gives the best features of both controllers. A few other details about feedback controller shown here. It can effectively eliminate disturbances for fast responding processes. But again, the downside is it waits until the disturbance has affected the process before corrective actions take. And then feedback loops can become unstable due to nonlinearity. And this is because the process is going to change significantly more than it would otherwise if a feed-forward action was implemented into the feedback control scheme. Okay, feed-forward control requires an additional measurement, which costs money. So feed-forward control is going to be additional sensors and controllers to measure one or more inputs. The purpose of feed-forward control is it compensates for a specific disturbance before it affects the process. In reality, feed-forward control cannot be used alone. So it has to be incorporated with feedback control because there's no such thing as perfect logic, perfect control of the system, perfect metering in order to prevent a process from reaching its constraint. When feed-forward is combined with feedback, it can improve process reliability. Right? Because again, one of the main things is that the feed-forward control is going to prevent the process from changing too much. So nonlinearities within a process can be not necessarily ignored, but they're not going to have as much of an effect because the process shouldn't change too far from its specified value. Feed-forward control works best with slow processes and maybe those with significant dead time. Okay, let's look at another example of feed-forward control, and this is on a heat exchanger. So if we look at a heat exchanger on its own, or heat exchanger with feedback control only, for a heat exchanger, we care about the temperature of the process stream coming out. That's the purpose of a heat exchanger. We want this to be at a specified value. And so in feedback control only is that the controller is going to change the amount of heating to the process to keep it at a specified value. So that's feedback control only. So for a heat exchanger, there are a variety of disturbances that can affect the process. If you want, you can pause, think about what those disturbances are, and then how we might mitigate the effect of one of those disturbances. The disturbance we care about is temperature. So we care about feed temperature. We know that if the feed temperature changes, it's going to affect the temperature coming out of the system. So if the temperature increases, we don't need as much heating. If the temperature decreases, we need more heating. So we can incorporate a feed-forward scheme that, as this temperature changes, we can open this valve before the process changes too much. Okay, so let's look at how that might work. We have our main feedback control loop. So we have our specified value going to our feedback controller. And again, without feed-forward control, this goes and changes the pressure. It changes the valve position on the steam. If the temperature changes, we can have a feed-forward controller. Now, we don't necessarily need a feed-forward controller doesn't have an input, so it just has a relationship between our disturbance measurement, which in this case is the temperature, and the steam. So that's going to be the algorithm of the feed-forward controller. So the feed-forward controller is going to also change the steam position, or change the valve position on the steam valve. So both of these want to change the valve position on the steam in order to keep it at a specified value. So because we can only send one signal to the control valve, what we're going to do is we're going to add these two signals together and change the valve position on the steam. Okay, so if there is no change in the process and we detect a change in the temperature entering the system, okay, this signal right here is going to be 0. But this signal right here is going to be a negative signal to close the valve. So if the temperature entering increases, the feed-forward controller is going to tell this valve to close before this process changes. Eventually now, this temperature of this system will change a little bit, but maybe this system won't change. So then in that case, this system becomes 0, and then this one is what does the control work on the steam valve. Also notice that this system is set up with a cascade control. So in this case, the ratio controller sends a remote set point to the pressure controller. We measure the pressure of the steam, which is related to the temperature of the steam. So if the pressure changes, this valve is going to open or close to keep this at a specified value. We don't necessarily have to have this cascaded, but in this case, it's shown as a cascade loop. So in this case, the feed-forward feedback both of them are cascaded, or the additive signal is cascaded to the pressure on the steam line. So the question for you here is, what disturbance is this cascade loop accounting for? Before I summarize, I want to talk about this next slide right here, which is feed-forward. So we didn't go into detail, and we're not going to go into detail on tuning a feed-forward controller, but this is something I'd like you to look at a little bit. So a feed-forward controller can be tuned, again, using probably like a field tuning method. So the process for tuning a feed-forward controller is discussed in section 12.4. And this is going to be related to feed-forward controllers eliminate the effect of a disturbance on the process. So we know the ratio, we know the gain on the feed-forward controller is going to be related to the gain on the disturbance and the gain on the process. The time constant associated on the controller is going to be related to the time constant of the process, time constant of the disturbance, and then the dead time on the feed-forward controller is going to be related to these two. You can look at the math here, but I want to just discuss in general how you tune a controller to achieve the process that you want. Okay, so in general, for when we have a feed-forward controller, if a disturbance affects the process, the feed-forward controller is going to minimize the effect of that disturbance. So what's going to happen is that the process is going to start to change, and then the feed-forward controller is going to cause the corrective action to occur to the process. So the feed-forward controller can be tuned in order to achieve the desired performance that you want. So as soon as the disturbance, so again, this right here is the control variable, so we're not measuring the disturbance here. But the feed-forward controller, these lead lag elements are designed such that the feed-forward controller can cause a corrective action to occur. So as we measure the disturbance, we can start having the disturbance change the manipulated variable, which is going to cause the process to change. Right? So we don't want the process to change too much by our feed-forward controller in the negative direction, because eventually what happens is we change our manipulated variable, it affects the process, and then eventually the disturbance combined with our manipulated variable is going to get our process back down to steady state. Okay, so the feed-forward controller, we cause the process to change a little bit before the actual process before the process responds to the disturbance. The process responds to the disturbance, and then the combined change of the manipulative variable and the disturbance is going to eventually level out. So these components of the feed-forward controller, the lead lag, can be tuned such that the controller, the amount that the process decreases and the amount that the process increases are about the same, or however you necessarily want your process to respond. Okay, so in summary, we talked about a few methods. So cascade control. So cascade can effectively eliminate disturbances. The inner loop has to be faster than the outer loop. And the inner loop has to accommodate or has to eliminate the effect of a disturbance that's associated with a manipulative variable. A ratio controller can provide better performance if the manipulative variable is proportional to the feed rate. So for ratio control, the manipulative variable or the disturbance has to be a feed flow, and this feed flow rate has to be proportional to the manipulative variable or the value of the manipulative variable. And then finally, we talked about feed forward. It can be effective for measuring disturbances in slow response and slow processes, or other types of disturbances that really can't be accommodated using cascade or ratio control. Okay, so for next time, what I want you to do is think about these examples, and we'll go through a variety of examples on the next lecture. So here's an example of a CSTR with a gas vent. And so we want to look at incorporating feed-forward control elements, so either cascade, ratio, or feed-forward, to eliminate the effect of specific disturbances that are discussed here. Also, I want you to look at problem 12.34. So here's an example. Here's a distillation column. Now, there are a variety of problems that are fairly similar. In this case, we want to look at incorporating cascade, ratio components into this system. And we'll also look at some feed-forward other types of systems as well. Okay, so that's going to do it for today. Next time, we're going to go through a variety of examples to both incorporate feed-forward, cascade, ratio control schemes into feedback control schemes. And we'll also discuss the effect of different types of feed-forward elements on the way processes respond. So we'll see you next time.